Hello friends, welcome back to my YouTube channel. Uh, in this video lecture, I'm continuing my discussion on distillation, and this is distillation part 16. In part 15, I had started my discussion on continuous rectification, and that was an introductory video on continuous rectification. In part 16, I'll be talking about material balance for a tray column. In my previous lecture, that is part 15, I discussed about how continuous rectification is carried out in tray columns. And in this particular lecture, now I'll be talking about how you can take material balance for a typical tray column in which continuous rectification is carried out. So let us begin the discussion. So uh, let me first tell you what is a typical tray column. So let this represent a tray column. So you can see these are the trays, the dashed lines that I have drawn over here. They represent individual trays in the tray column. So I have given numbers to those trays. The topmost tray, I'm calling it as first tray or first plate, the topmost tray. It is the first plate, and the last plate in the column, let it be nth plate. So that means in this tray column there are n number of plates. Then you have the feed plate, the plate on which feed is introduced into the column. So this will be the feed plate. Then any plate in the rectifying section, that is section above the feed plate, let us consider any plate, nth plate, small nth plate. Then in the stripping section, that is in the section below the feed plate, I'm considering any plate. I'm calling that as mth plate, and next plate would be m plus 1th plate. Okay, so I'll be following these notations in my discussion. So you have first plate, the topmost plate, capital N plate, the last plate in the column, and in between those two plates, I'm considering any nth plate in the rectifying section, any mth plate in the stripping section. The plate or tray next to mth plate will be m plus 1th plate. Okay, so as the feed enters the columns, it will be as the feed enters the column, it will be flowing down to the reboiler. So I have shown the path. Then in the reboiler, heat will be added so as to cause boiling of the solution. The resulting vapor phase is admitted at the bottom of the column, and then that vapor phase rises through the column. It rises through the column and it is taken out from the top. Then it is sent to the condenser where heat is removed and you get the condensate, and then the condensate is divided into two parts. One goes back to the column, whereas the other is taken out as the product. The product will be distillate, that is top product. We are going to identify this distillate by using this notation. Then the other fraction that goes back to the column, we call that as reflux. So after entering the column, the liquid will be flowing down, and then on the feed plate it will be getting added to the feed that is coming into the column. So while the column operates, liquid phase and vapor phase, they will be in contact with each other. Then from the reboiler, we are taking one more product, and that is nothing but a residue, or you call it as bottom product, and it will be identified by this letters, notations, W and XW. I will tell you what are these notations. Okay, so this is how we will be discussing a typical tray column. With this notation, we are going to take material balance, and that we are going to understand material balance for this tray column. Okay, so in my previous lecture I have discussed the section above the feed plate. We call that as a rectifying section, and the section below the feed plate we call that as stripping section. Okay, so let us now move ahead. So the notations that we are going to use, let us understand the feed solution. The feed solution is nothing but a binary liquid solution of two components. Which are these two components? Component A and component B. Out of A and B, A is the more volatile component. That is, A is having a lower boiling point and higher vapor pressure if you compare that with B. Then F, it represents the molar flow rate of feed, which will be, for example, it will be kilomole per hour, for example, or it could be kilomole per second. So it is molar flow rate. And then the other notation, XF, is mole fraction of A, that is mole fraction of more volatile component in the feed solution. Then the distillate or the top product. For distillate, capital D represents its molar flow rate, and XD represents mole fraction of A in the distillate, that is mole fraction of more volatile component in the distillate. Okay, now the residue or the bottom product, we just understood how feed solution is represented and then how distillate is represented. Now let us know how residue or the bottom product is represented. For residue or bottom product, W represents the molar flow rate and XW represents mole fraction of A in it, that is mole fraction of more volatile component in it. For reflux, L0 will be its molar flow rate and XD will be mole fraction of A in it. So you must have noticed that mole fraction of A in the reflux is same as that in the distillate, because after condensing, the condensate is simply divided into two fractions. So both the fractions will be having same composition. That's why in reflux also mole fraction of A will be XD. Then the reboiler, for reboiler, QR will represent the rate of heat addition in it. The heat being added to boil the solution so as to create a vapor phase out of it. Then you have for condenser, QC will represent the rate of heat removal from it. A rate of heat removal from the vapor phase so as to bring about the condensation. So QC will represent the rate of heat removal in the condenser. So these are the notations that we will be using for in our discussion. Okay, now first we will discuss material balance for the rectifying section. So rectifying section, as you know, that is the section above the feed plate. So what I will do, we have the column, and now we are going to talk about the rectifying section. So that is, now I have covered that section, rectifying section, by using this pink envelope. Now I have enlarged that portion. So rectifying section, we will have any plate, any nth plate in it, then the first plate, then you have the condenser. So condenser, in condenser heat is removed, QC, heat is removed at the rate of QC. The condensate is divided into two fractions. Reflux, L0 will be its molar flow rate, XD will be mole fraction of more volatile, that is A in it. Then distillate or top product, D will be its molar flow rate and XD will be mole fraction of A in it. Okay, now let us move ahead. Now first let us know how to take material balance for the condenser. So for that again I have shown this schematic. So the notations, now just let me tell you what are this notation. Now this is the liquid stream that is coming from plate number 1. So it will be identical, it will have molar flow rate L1 and X1 will be mole fraction of A in it, that is more volatile component. Then the liquid phase that leaves plate, nth plate, will have a molar flow rate of Ln and mole fraction of A in it will be Xn. Then the vapor phase that is leaving nth plate will be identified as the molar flow rate for that stream will be Gn and mole fraction of A in it will be Yn. Similarly, for the vapor phase that rises out of tray number 1, molar flow rate will be G1 and mole fraction of A in it will be Y1. Then same vapor phase, that is vapor phase from the top tray is taken out, so it will have the same flow rate G1 Y1. Then it will be moving to the condenser where it will be condensed, and then you will be getting reflux and then the distillate. Now we are going to consider only the condenser. To begin with, we are going to consider condenser and we will be discussing material balance for it. Okay, so now let me tell you, let me discuss it. Okay, so you have the condenser over here. I have shown the diagram. Total material balance. It will be steady state material balance. What I am discussing is steady state material balance. That is, there will be no accumulation. Whatever material goes into the condenser, it is coming out. Okay, so if you look at the envelope, pink envelope that I have taken around the condenser, you just identify the streams, material streams that are associated with it. So one is G1, one is the stream with molar flow rate G1 that is entering the condenser. Then two streams are coming out of it, two material streams are coming out of it. One is the distillate that comes out at a molar flow rate of D, and the other one is reflux that is coming out of the envelope at a molar flow rate of L0. Okay, so the total material balance will be material input. The rate of material in is equal to rate of material out. So material is entering, material in the form of vapor is entering at a rate of G1, that is equal to material is leaving out in the form of a reflux and distillate. So it will be simply G1 is equal to L0 plus D, no accumulation. We are considering a steady state material balance, let me tell you. So this is steady state material balance. What do you mean by steady state material balance? Material balance taken where accumulation is zero. There is no accumulation. So the balance will be simply input is equal to output. So this is input and this is output. Input material is equal to output material. Then we will take material balance for A. Why A? Is the more volatile component. A is the more volatile component. Okay, so material balance for more volatile component. Again, we are going to take it at a steady state. Input is equal to output. That is, input of A is equal to output of A. So input of A will be A is coming or A is going into the envelope. along with this vapor stream. So total flow rate is G1. Y1 is mole fraction of A in it. So moles of A will be fraction into total. So that's why you have this term G1 into Y1. So input of A, that is equal to A is coming out along with the reflux and then the distillate. So it will be total reflux into fraction of A in it, that is L0 into XT, plus total distillate into fraction of A in it, that is D into XT. Okay. So steady state material balance for A will be given by this equation. G1 Y1 is equal to L0 into XT plus D into XT. Okay. So little manipulations will do with it. So what we have done, so we can see out of these two terms XD is common in. So you can take XD as common out of those two terms. So it will be G1 Y1 is equal to L0 plus D into XT. Then we can in the next step, what I have done, I have divided with L0 throughout the equation. So it will be G1 upon L0 into Y1, that is equal to 1 plus D upon L0 into XT. So what is done in this case? So it will be L0 on, if you look on the right hand side of this equation, it will be L0 upon L0. So L0 upon L0 is 1. So if when you are dividing, let me just tell you. So it will be L0 upon L0 plus D upon L0 into XT. So this will be 1. So that's why you have 1 over here. So the equation will be G1 upon L0 into Y1 is equal to 1 plus D upon L0 into XT. And I'm calling that as equation number 3. Now in this equation, in equation 3, you have this ratio L0 upon G1. So this ratio is said to be the internal reflux ratio, and let us denote it by R dash. Whereas the other ratio, which is that L0 upon D, it will be the external reflux ratio, and we are going to denote that by R. Okay. So at this point of time, we have understood two different reflux ratios. One is L0 upon G1, which is internal reflux ratio, and the other one is L0 upon D, which is external reflux ratio. Internal reflux ratio, we are going to denote it by R dash, and external reflux ratio, we are going to denote that by R. So if you use those notations in equation number 3, you will have this equation. So G1 upon L0 is nothing but 1 upon R dash, because R dash is defined as L0 upon G1. So G1 upon L0 is 1 upon R dash, that is equal to 1 plus, since L0 by D is R, D upon L0 will be 1 upon R. So it will be 1 plus 1 upon R into XD, and I'm calling it as equation number 4. Okay, so after taking material balance for the condenser, we have got two, you can say, new concept. We have understood two new concepts. One is internal reflux ratio, which is nothing but the ratio of reflux to the vapor flow that goes into condenser. And then you have external reflux ratio, which is nothing but ratio of reflux flow to the distillate flow. Okay, now let us move ahead. Now continuing, now let us understand how to take material balance for the entire rectifying section. We just learned how to take material balance for condenser, which is a part of rectifying section. Now let us take material balance for the entire rectifying section. And now I'm showing the rectifying section. Now the notations I have already explained just now, so we'll follow the same notations in this discussion also. Okay, now if you just look at tray number n, so you have two streams associated with it. One is the liquid stream that is leaving it at a flow rate of Ln, then the other one is the vapor phase that is leaving it at a flow rate of Gn. Now the stream that is coming to nth plate, the liquid will be coming from the tray above it, that is n minus 1th plate, and vapor will be coming from a tray that is next to nth plate or nth tray, so that will be n plus 1th tray. So that's why you have the vapor flow that is coming from tray next to nth tray, that is n plus 1 tray. It will be having a flow rate of Gn plus 1, and Yn plus 1 will represent mole fraction of A in it. Okay, so now for taking material balance for the rectifying section, we are going to consider this envelope. If you look at this envelope and try to identify the material streams associated with it, so you can easily identify those material stream. So this is material. Let me number those streams. So this is stream number 1, material stream that is entering the rectifying section. This is stream number 2, material stream that is leaving the rectifying section, and this is stream number 3, the material stream that is leaving the rectifying section. So you have 3 material streams. One is the liquid that is coming out of it, liquid stream coming from nth plate. Then you have stream number 2, which is nothing but the vapor stream that is going into the rectifying section. And then you have the third material stream, that is the distillate stream that is coming out of the rectifying section. Okay, so I hope this is clear to you. If you have any doubt regarding this, you please let me know in the comment section. Okay, so with this understanding, now let us take the material balance. Again, we are discussing material balance at steady state. Input is equal to output. Now you can easily tell the material balance will be written as it is given in equation number 5. So it will be Gn plus 1, that is input, is equal to output. There are two outputs. One is Ln. So Gn plus 1 is equal to Ln plus D. Input is equal to output. Similarly, material balance for A. Why A? Because A is the more volatile component. Material balance for A at steady state. So we are discussing the material balance at steady state. You please remember, we are not considering accumulation. So it will be Gn plus 1 into Yn plus 1, that is equal to Ln into Xn plus D into Xd. Total material stream going into fraction of A net, Gn plus 1, Yn plus 1, that is equal to Ln into Xn plus D into Xd, and I'm calling this as equation number 6. And if you rearrange equation number 6. So how the rearrangement is done? We are taking this term, Gn plus term, on the other side, that is the right hand side of this equation. So you will have Yn plus 1 is equal to Ln upon Gn plus 1 into Xn plus D upon Gn plus 1 into Xd, and I'm calling it as equation number 7. And what else you can do? You can use equation number 5. What does equation number 5 gives us? It gives Gn plus 1. So you can use Gn plus 1 as we have written in equation 5 in equation number 7. So you get yn plus 1 is equal to ln upon ln plus d. Now you can just check gn plus 1 is replaced with ln plus d according to equation 5. So yn plus 1 is equal to ln upon ln plus d into xn plus d upon ln plus d into xd. Let me call this as equation number 8. Now if you look at equation number 8, what can you say? Equation number 8, it will represent a straight line. If you plot x, that is mole fraction of A in liquid phase versus mole fractions of A in vapor phase, whatever plot you get, equation number 8 will be representing a straight line on it. Okay? And slope of this straight line is ln upon ln plus d. So this equation is of the form y is equal to mx plus c. This is a straight line where in this equation m is the slope and c is the intercept. Okay? So if you compare this form of line with equation 8, you will come to know that for this line slope is ln upon ln plus d, whereas this will be the intercept. This will be the intercept. Okay, so that's why equation number 8, which is representing a straight line, will have a slope of ln upon ln plus d. Then intercept is d upon ln plus d into xd. This will be the intercept, and this line is nothing but the operating line for the rectifying section. So this line will describe operations in the rectifying section. A straight line with slope ln upon ln plus d and intercept on y-axis. So if you have to know how the line will look, so if you are plotting y versus x, you'll be getting a straight line and slope will be m for this line, and intercept made by this line on the y-axis will be c. So in this case m is ln upon ln plus d and c is d upon ln plus d into xd. I hope this is clear to you. Okay, now let us move ahead. So that ends our discussion for material balance for the rectifying section. Now let us understand material balance for the stripping section. So for that, let us now again look at the column. Now we know stripping section is nothing but the section of the column below the feed plate. So we are talking about it. So I'm again taking a pink envelope. So that is covering the section below the feed plate, that is the stripping section. Now I have enlarged that section. So you have various plates. So you have mth plate, then plate next to m plate is m plus 1 plate, and last plate is nth plate. And then you have the reboiler. So first we'll understand material balance for the reboiler. So for that, let us look at the reboiler. Let us follow the notations. The notations that I'm going to use for this discussion is, so for example, for the liquid stream that is leaving mth plate, the flow rate, liquid flow rate will be L bar m. So this bar is used in order to convey to you that the flow rate, liquid flow rate in the rectifying section is different from liquid flow rate in the stripping section. And why m? Because it indicates the liquid that is leaving that particular tray. So the liquid flow rate will be, molar flow rate for the liquid leaving m plate will be L bar m. Mole fraction of A, mole fraction of more volatile component in it will be xm. Okay. Similarly, the other notations. Let me just show you. Now the stream that is leaving m plus 1th plate will have a molar flow rate of L bar m plus 1 and mole fraction of A in it will be x m plus 1. Then the liquid stream that is leaving the last tray, nth tray, will be having a molar flow rate of L bar n and mole fraction of A in it will be xn. Then it will be the same stream will be taken out and sent to the reboiler. In the reboiler, heat will be added at a rate of QR and it will generate the vapor phase. So the vapor phase, now you just look at the notation. Vapor phase that is coming, now reboiler is actually, you can consider it as a plate next to nth plate. So it will be n plus 1 plate, and vapor phase that is coming out of it will be represented as G bar n plus 1. Again, bar over here indicates vapor flow in rectifying and stripping sections, they are different. So G bar n plus 1 into Y, the yn plus 1 will represent mole fraction of A in it, mole fraction of more volatile component in it. Okay. Then this will be the vapor phase that is leaving nth plate. So it will be G bar n, Yn. And then this will be the vapor stream that is leaving m plus 1th plate with flow rate G bar m plus 1. Mole fraction of A in it is Ym plus 1. And finally, you have the vapor flow that is leaving mth plate. It will have flow rate of G bar m and mole fraction of A in it will be Ym. Okay, so in my discussion I am going to use this notation. So first, as we said, we are going to consider material balance for the reboiler. So if you look at the reboiler and try to identify the material streams, so you'll come to know that there are three material streams. One is having a molar flow rate of L bar n, and what is this stream? This stream is going into the envelope. Okay, the other stream is G bar n plus 1, the vapor phase that is coming out of the reboiler. So this is coming out, and there is one more stream that is the residue or the bottom product. It will have, or it is having molar flow rate of W. Again, this is coming out. Okay. So with this understanding, now let us look at the material balance. Again, I have shown the reboiler. Now let us take total material balance. Again, we are discussing it at steady state. Input is equal to output. Material balance at steady state. Input is equal to output. So as I said, input is G bar n plus 1. So G bar n plus 1 is equal to L bar n plus W. Input is equal to output. Similarly, material balance for A, the more volatile component. So it will be G bar n plus 1 into Yn plus 1. That is equal to L bar n into Xn plus W into Xw. Total into fraction. Again, material balance for A at steady state. Then that ends material balance for the reboiler. Now let us talk about material balance for the entire stripping section. So that means now we are going to consider this envelope. So total material balance for the entire rectifying section. Again, for if you have to identify the streams, if you consider the entire rectifying section, then this is one stream that is associated with it, L bar m, and this is going into the envelope. Then which is the other stream? This is second stream, G bar m plus 1. It is going out of the envelope. And the third material stream is W, that is going out. So total material balance at steady state, in is equal to out. L bar m is equal to G bar m plus 1 plus W. So continuing with our numbering, this will be equation number 11. Similarly, material balance for component A, total into fraction. So it will be L bar m into xm, that is equal to G bar m plus 1 into ym plus 1 plus W into xw, and I am calling it as equation number 12. And so from equation number 12, you can write this, you can rearrange it in this way. G bar m plus 1 into ym plus 1, that is L bar m into xm minus W into xw. So what I have done, I have brought this term on this side to get this equation. Okay. So again, if you rearrange it, so it will be the G bar m plus 1 is brought on the other side, that is right hand side. So it will be ym plus 1 is equal to L bar m upon G bar m plus 1 into xm minus W into G bar m plus 1 W upon G bar m plus 1 into xw. Okay, so let us continue with that. Material balance for the entire stripping section. From the previous slide, you have this equation: ym plus 1 is equal to L bar m upon G bar m plus 1 into xm minus W upon G bar m plus 1 into xw. This is equation number, let us call it as equation 30. Now we are going to use equation 11 that was previously obtained, and over here I am rewriting that equation. So equation 11 is L bar m is equal to G bar m plus 1 plus W. So from this I can get G bar m plus 1 is equal to L bar m minus W. That is, this term is taken to the other side. So you get this. Now what will be our next step? In the next step, we are going to use this G bar m plus 1 in equation 13. That means in place of G bar m plus 1, we are going to use L bar m minus W. So it will be ym plus 1, that is equal to L bar m upon L bar m minus W into xm minus W upon L bar m minus W into xw. So we have replaced G bar m plus 1 with L bar m minus W. Now if you look at equation number 14, you'll come to know that it represents a straight line on a XY plot. The slope for this line will be L bar m upon L bar m minus W, and intercept will be minus W upon L bar m minus W. Again, this line, if you plot it on XY plot, it will be a straight line, and slope for this will be L bar m upon L bar m minus W, and intercept on it will be a negative intercept, in this case minus W upon L bar m minus W. Okay, so this is nothing but, or this straight line is nothing but operating line for the stripping section. Why operating line? Because this line, if you follow the line on XY plot, it is going to describe the operation within the stripping section. Okay, then if you take material balance for the entire tray column. Now let us understand how to take material balance for the entire column. So I am showing the entire column, and now we are going to talk about material balance for the entire column. So if you look at the entire column and try to identify the material streams, so you can identify the stream. The feed, second one is the distillate, and third one is the residue. Okay, so first stream, that is feed stream, is going into the column. Second stream, that is distillate, it is going out of the column. and third stream, that is the residue stream, again it is going out of the column. Okay. So total material balance at steady state, of course, which is input is equal to output. So input is F feed, output is distillate and residue. So it will be F is equal to D plus W, and I'm calling it as equation number 15. And what is left? Material balance for A, that is material balance for the more volatile component. So it will be F into XF, that is equal to D into XT plus W into XW, and I'm calling it as equation number 16. So in this way, you can take material balance for the entire column. Okay, so with this, I end my discussion for the present topic, which was material balance for a typical tray column. So we have understood material balance, how to take material balance for the rectifying section, how to take it for the condenser, then for stripping section, material balance for the reboiler, and now how to take material balance for the entire tray column. Again, you just remember, we have understood material balance under steady state conditions. Now we know what is internal reflux ratio, what is external reflux ratio, what is the equation, what is the operating line for rectifying section, operating line for stripping section. Okay, so with this I end my discussion for today's video lecture. Thank you for being with me. Thank you for watching my video. I hope you have subscribed to my channel. If not, you please subscribe to my channel. Tell your friends to subscribe to my channel. Do watch my videos. Do like my videos. Please give your feedback in the comment section. In my coming video lectures, I'll be continuing my discussion on continuous rectification. For now, it's bye bye. Have a nice day and be with me. Thank you.